and today I'll be going over one of the projects I've done that compares different ML models together. Specifically, it goes over four types of ML models: supervised, semi-supervised, semi-supervised generative adversarial networks, and variational autoencoders. And we're going to be looking at all four of these models, and we're going to see which one is most accurate in classifying melanoma images. So really quickly, if you want to do this project yourself, here are some of the prerequisites you might want to have before starting it. So this project is generally intended for people that have a little bit of an intermediate Python experience. They know how to use functions, they know how to use import statements and stuff like that. And you should have a little bit of experience with deep learning. You should know the how convolutional neural networks work, how image classification works. You should also kind of know how neural networks in general work. Um, you should also kind of some knowledge about PyTorch and TensorFlow. Some of the other tools we'll be using during this course are NumPy, Matplotlib, PIL, and CV2 as well. So here are the libraries that we used during doing our project. So we first used PyTorch, and this is one of the most popular and fastest growing deep learning frameworks. We also use Torch Vision, which is used for computer vision. We use NumPy, which is used for scientific computing and also storing specific values. We use sklearn for data science and ML models. We use Matplotlib for data visualization. And then we use TensorFlow for building the semi-supervised GAN framework. So um, the dataset that we trained on had around 7,900 images. There were 200 labeled images, there were 600 test images, and there were around 7,018 unlabeled images. So this is kind of how the supervised and semi-supervised models work. So a supervised model would train on the labeled dataset, while the semi-supervised model would use both the labeled and the unlabeled dataset. And the test dataset is used for evaluating our model and seeing if it's actually working. All these images are in 32 by 32 JPEG files, but as you'll see below, I actually resized the images to 100 by 100 pixels, because it made it much easier and made the convolutional neural network much more accurate. The naming convention we did is as follows. We said each file name is ending in at least zero, is ending in 0 or 1, where 0 is a melanoma negative individual and 1 is a melanoma positive individual. So the dataset can be found over here. It will be provided in the description below. So let's go into the actual project. So actually comparing these different ML models together. So since there are only around 200 labeled images to work with, I actually had to perform data augmentation on the training images by changing their contrast, brightness, sharpness, and color, so that we can have larger batch sizes and a larger training data set to work with. And additionally, like I said before, all the data was resized to a 100 by 100 pixel image so that the training time of the model was reduced. So first we'll be going over what I did for the supervised image classifier. So I used a TensorFlow backend, and I achieved an accuracy of around 75% by doing hyperparameter tuning and playing around with the complexity of the CNN. So here are the steps I took to implement the model. So first, I built testing and training image data generators, and I fed images into the model in batches, and I took a batch size of 32 at the ending. I defined different layers, so I used 2 convolutional layers and 4 max pooling layers, and then I trained the model using 10 epochs, and I ran this code in training a supervised image classifier.ip1b, so I'll quickly just run through that too. So here are my import statements, and over here is me defining the model. The image data generators over here. We're training the model over here, and we're doing evaluation on the testing dataset over here. So here's just all the images, and if you look over here, the final output was 449 out of 599 that were correctly classified, so we had around a 75% accuracy rate. Next, we're going to be looking at a semi-supervised image classifier. So the semi-supervised classifier achieved an accuracy of around 75%, similar to the supervised image classifier. And here are the steps that are taken to implement the model. So first I trained an image classifier that was around the same steps as was outlined above in the supervised image classifier. But now I added an extra step. I actually ran predictions on the trained supervised image classifier on the unlabeled dataset. I took those labels that were predicted by the supervised image classifier, and I attached them to the unlabeled images, and I ran the model with both the labeled unlabeled data and also the original labeled data. And I found the accuracy by running it on the testing dataset, and I found that it had an accuracy of around 75%, and this was actually really similar to the supervised image classifier. And the model once again used a TensorFlow with a Keras backend to run. And the semi-supervised image classifier was generally the same as the supervised image classifier, just a few differences. Um, so next we'll be going over to variational autoencoders. So unfortunately, because of computational expenses, I had to train the model on the MNIST dataset because there wasn't enough capacity on my computer and running it on Google Colab to actually run with the melanoma detection dataset. Um, but here's the steps I did to implement the model. It's relatively similar for the melanoma detection. So you said to change of the image size and maybe just like refine the encoder and decoder a little bit. So here are the steps I took to implement the variational encoder model. So I first read in the MNIST dataset, defined training and testing sets, and I determined the activation function I was going to use. So I decided to use linearized ReLU instead of ReLU. And the reason I did so is because linearized ReLU actually allows it doesn't drop your function to 0 automatically, and it actually makes sure that more of your neurons stay active. So I then created the encoder using a series of convolutional and dropout layers. Next, I created a decoder using a series of dense, convolutional, and dropout layers. And then I finally compiled the model using an atom optimizer. I trained the model and I evaluated the images created by the decoder. And the final model used a TensorFlow with the Keras backend to run, similar to the semi-supervised and the supervised image classifiers. And the code is stored in variational autoencoder for MNIST dataset. There's two of these. There's actually a no training output and a training output one. So this one actually has the training and all the different images. Has the no training that has no training output, but just shows you the final results. So if you scroll down to the bottom over here, so here's what we used to actually show the images. So we just took random we just took in a random noise, and I basically put it through the encoder decoder, and it outputted MNIST dataset images. The last thing that I made was a semi-supervised generative adversarial network, and this used a TensorFlow and Keras backend. This achieved an accuracy of around 50%, and the most probable reason for why this was such a low accuracy was probably because the discriminator is much more powerful than the generator, and I wasn't able to figure out exactly why, even though I had tried out a bunch of different things. So hopefully this is something that you guys can actually um, do in your own code to actually figure out what was going on with that. So here are some of the steps I took to implement the model. So I built training and testing image data generators using a class to feed images into the model in batches. So instead of using a batch size of 32, I used a batch size of 16. So next I built a generator network. So this generator network had 3 convolution layers, hyperbolic tangent activation function at the ending. Next, I built a discriminator network that had 3 convolutional layers again, and it had leaky ReLU as its activation function, and it used batch normalization. Next, I built the unsupervised and supervised discriminators from the discriminator network that was created above. And the unsupervised discriminator used a softmax layer because softmax is used to confine probabilities from 0 to 1. And the unsupervised discriminator has to determine whether the image was real or fake. And in the supervised discriminator, I used a defined predict function, so that's basically going to determine whether the image whether the image contains a person with melanoma or without melanoma, and that was my defined predict function. So the supervised discriminators actually we're trying to optimize over here because we want to see how good the model is at predicting melanoma, and the unsupervised discriminator is actually what competes with the generator to produce the best supervised discriminator. So over here, we say we build the generative adversarial network, combining both the generator and the discriminator network, and I trained the model using around 500 iterations. I also tried 8,000 iterations, but I found that I just overfitted the model. So I would suggest playing around with that a little bit, just seeing how much iterations works for you. And then I evaluated the model using the testing set. So the final model can be found in semi-supervised GAN.ipynb. So after doing a lot of research on this, I've realized that semi-supervised models are generally better than supervised models because even though you're just labeling unlabeled images with your supervised image classifier, it actually on average tends to increase the accuracy. And one reason why this probably didn't increase the accuracy for the melanoma dataset is because the melanoma dataset was so small, so it wasn't able to it wasn't able to it was so small compared to the unlabeled dataset that the unlabeled dataset probably took over the labeled dataset. The semi-supervised generative adversarial networks are actually better than supervised models, and if you play around with that, we actually I was actually able to achieve an accuracy of 80%. Variational autoencoders are generally tied in level with semi-supervised generative adversarial networks, and it generally just depends on what you want to do with the code. So definitely try out both of them, and both of them are similar in complexity and difficulty. So but I found that the variational autoencoder actually took a little bit longer to run, so maybe keep that in mind. So in the ending, the result of this project were I found that semi-supervised generative adversarial networks were the best at classifying melanoma images with an accuracy of 80%, but they were the most difficult to optimize. Variational autoencoders were next, but those took the longest to run. Semi-supervised was next, because they have an unlabeled dataset that they're adding to the model, and then supervised models performed the worst with an accuracy of 75%. Thank you for watching.